In this video, we will present our work entitled Sim-to-Real Deep Reinforcement Learning for Safe End-to-End Planning of Aerial Robots. Autonomous aerial robots are increasingly deployed in applications that require safe path planning in dense environments, such as a forest or a greenhouse. In this study, a novel end-to-end path planning algorithm is proposed for aerial robots in dense environments. We consider a quadrotor with a forward-facing depth camera and informed about a rough global path. The navigation problem is introduced in an episodic setting to enable reinforcement learning. At each time step, the agent receives the depth image and the target point on the global trajectory, and takes an action to transit to the next time step. We trained the end-to-end planner as a neural network policy with deep reinforcement learning. Using the depth image and the moving target as observations, the policy generates continuous actions as the direction of the 1 meter position step and the heading angle. We also select 7 actions to form a separate discrete action set as a baseline. The end-to-end agent is rewarded proportional to approaching the target pose and punished if the safety boundaries are violated. The episode is terminated in case of deviation from the global trajectory, collision, or completing the track without crash, with associated rewards. Training is handled in VBOT simulations on a 30-meter length route. The obstacles are randomized in shape, position, orientation, and size for every episode. The quadrotor is transported in VBOTs every time step without dynamics for computational purposes. The method is evaluated in 6 fixed scenarios obtained randomly. Each method runs 10 trials for each scenario. Pilot software-in-the-loop dynamics are integrated for tests. Comprehensive evaluations show that our method SCDP has a better performance in terms of success rate and distance traveled when compared to deep reinforcement learning-based and artificial potential field-based planners in simulations. We have also transferred the trained policy from simulation to real-time experiments. We built the custom quadrotor, deploying an Intel depth camera, a Jetson TX2 onboard computer, and a Pixhawk flight controller. The overall framework runs entirely on board with 6 Hz, except the robot's localization is provided by a motion capture system. We set 2 8-meter length scenarios. In the moderate scenario, multiple obstacles are collected in 2 regions. For the difficult case, we distribute 8 obstacles around the lab area. We tested our method SCDP and the baseline DDP in 5 trials in each scenario and reported. Our method fails only once in the difficult scenario. On the other hand, DDP encounters a collision in both scenarios and leave the global path in remaining 4 trials in the difficult case. To sum up, we propose a VBOT simulation-based RL framework, including highly randomized obstacle configurations, enabling safe end-to-end planning. We also analyzed the effect of proposed safety boundaries in comprehensive simulations, together with a comparison with learning-based and conventional baselines. Finally, we demonstrate the planner in highly occluded real-time experiments by direct sim-to-real transfer. Thank you for listening.